Lewis diagrams are diagrams that we use to try and show the shapes of molecules and where those electrons exist in those molecules. So there are certain steps that we're going to use to draw these Lewis structures, and you'll also be doing a lab where you'll be putting together a lot of the Lewis structures, so you'll be able to see them in a three-dimensional format. Basically, atoms like to have 8 valence electrons. And so most atoms don't have 8 valence electrons, so they like to share their electrons with other atoms in order to give each one 8. It's something that we call the Octet Rule. And the Octet Rule basically tells us that atoms form these bonds in order to obtain 8 valence electrons, or at least share enough electrons so that each one has 8. The reason they want to have 8 is because that makes them stable. It gives them a full energy level between the S and the P blocks. The noble gases already have 8 valence electrons, and that's why they don't need to bond with any other elements in order to increase their stability, because they are already stable. They already adhere to the Octet Rule. So here are the steps for determining Lewis structures. First step is to determine the total number of valence electrons an atom has. The easy way to do that is to look at the group that it is in on the periodic table. Group 1 elements have 1 valence electron. Groups 2 through 12 have 2. 13 has 3, 14 4, 15 5, 16 6, 17 7, and group 18 has 8. If you look at the group number, that will give you the number of valence electrons. And you're going to add all those up. Then what we're going to do is take the elements that you have given, and we're going to arrange them on a page. Usually, if you have a single element of one, that's the one that's going to go in the middle, and the other elements go around the outside. Sometimes it's trial and error to determine what's the best arrangement for the atoms. But the more of these you do, the easier it'll get to determine that. Anytime a bond is formed between two atoms, that takes 2 electrons. Electrons always travel in pairs. So if we want to form a bond between 2 atoms, you have to take 2 electrons. And by the way, when you add up the total number of valence electrons, it should always come out to an even number. Since they always travel in pairs, you always got to have an even number of electrons. And then the last step is we take our remaining electrons after we've formed bonds between the atoms and distribute it to each atom in order to make sure they all have 8 electrons around them. Now there are some exceptions. We're not going to worry about those too much. There is one exception we really have to take into consideration. But we'll deal with that on the next slide. So these are the steps for drawing Lewis structures that we'll go through each time that we draw one of these. And then if you get to a point where there aren't enough electrons to go around to give each atom 8 electrons, then we need to share some electrons in the bonds. So this is where double or triple bonds come into play. And we'll do some examples of those. So here's the one exception where we're going to have to watch out for, and that's hydrogen. Hydrogen only ever can hold 2 valence electrons. It brings 1, but it can form a bond with other elements to have 2 valence electrons, but that's it. It cannot have 8 electrons because hydrogen only has electrons in the 1s orbital. If you'll remember, the 1s orbital can only hold 2 electrons. So like for the Lewis diagram for water, as you see here, oxygen can have 8 around it, but hydrogen can only ever form a bond. It can't have any what we call lone pairs. And we'll do some examples of those. The other exceptions we're not going to concern ourselves with a whole bunch. So boron has a lot of exceptions, and some of the elements in period 3 and below, as you see here, sulfur, phosphorus, and xenon, can actually have more than 8 valence electrons. If this is something that really interests you and you take AP chemistry next year or second year chemistry, then we'll study the exceptions a lot more than we will this year. And there are some instances where we can have an odd number of electrons, but that leads to an extremely unstable molecule. So let's look at our first example. Carbon tetrafluoride, CF4. So that 4 tells us that we have 4 fluorine atoms and 1 carbon atom. So the first step that we have is to add up all the valence electrons for carbon and for fluorine. So carbon is in group 14, so it has 4 valence electrons. Fluorine's in group 17, so each fluorine atom has 7 valence electrons. There's a total of 4 fluorine atoms, each one with 7, so that's a total of 28, plus the 4 for carbon. So that gives us a total of 32 electrons that we need to show in our Lewis structure. So the first step is to arrange the atoms. If you have a single atom, that one goes in the middle. The technical rule is that the least electronegative atom goes in the middle. Of course, carbon has a lot lower electronegativity than fluorine, so that goes in the middle. We're going to arrange the 4 fluorine atoms around it. We need to take 2 electrons each to form a bond. So we need to form 4 bonds around the carbon, each one with 2 electrons. So that takes a total of 8 electrons just to form those bonds. Now carbon has an octet of electrons. It's done. It cannot hold anymore. So we have 24 electrons remaining, and we have to make sure each fluorine atom has an octet of electrons. Each fluorine atom right now is sharing 2, so each fluorine needs 6 more electrons. So we're going to show those electrons in pairs of dots. Remember a couple chapters ago doing the electron dot notation? That's why we did that then. And we're going to show those 3 lone pairs of electrons around each fluorine atom. So now each fluorine atom has a total of 8, and the carbon has a total of 8, and we used a total of 32 electrons, and that is the Lewis structure for carbon tetrafluoride. Let's look at another example. Carbon dioxide, CO2. 1 carbon atom and 2 oxygen atoms. That gives us a total of 16 valence electrons that we need to use. So if we lay it out, put a bond between each carbon and each oxygen, that takes 4 total electrons. We have 12 more to use. If we use those 12 and give each oxygen an octet, that's great. Each oxygen has an octet, but carbon only has 4 electrons around it. It needs 8. And we've used all our electrons. We don't have any more electrons to use on the carbon. So here's a case where we need to take 2 electrons from each oxygen atom, and we need to share them with the carbons. And by that, we're going to form a double bond between the carbon and each of the oxygens. That gives the carbon atom an octet of electrons, and it gives each oxygen an octet of electrons. So the carbon dioxide molecule has 2 double bonds, one between each carbon and the oxygen, using a total of 16 electrons, and it gives each one 8, fulfilling the octet rule. That's the Lewis structure for carbon dioxide. If we have ions, what we call polyatomic ions, meaning ions with a charge, we're going to use that charge to either add electrons or subtract electrons. If the ion has a negative charge, we're going to add an electron for each negative charge. If it has a positive charge, we're going to subtract an electron for each positive charge. That's the only difference. And we have to place brackets around the ion in the end. So if we look here, the ClO4 -1 ion, we're going to add up the chlorines. One of those each with 7. So that's 7. We have 4 oxygens, each with 6. So we add that up, we get a total of 31 electrons. Now that should tell you something's a little wrong, because you can only have an even number of electrons. Because it has a -1 charge, we're going to add 1 electron to that. Gives us a total of 32 electrons. Now that's going to be much easier to represent. We use 8 electrons to bond the oxygens to the chlorine. That leaves 24 left. We can distribute those around each oxygen to give each oxygen an octet. And now we got to put it in brackets and put a -1 charge on the outside to show that this whole species has a -1 charge. If we have the ammonium ion, for example, with a +1 charge, when we add up all the electrons for nitrogen and hydrogen, we get 9. We're going to subtract an electron because it has a positive charge. Remember, a positive charge means it's lacking an electron. So the NH4 has a total of 8 electrons. We're going to use all those to form the bonds. And remember, hydrogen only ever needs 2 electrons around it, so it's good. Nitrogen has an octet, and so we're going to put the brackets around it with a positive charge on the outside. Resonance structures occur when we can't use a single Lewis diagram to draw the structure. So an example down here is the ozone molecule, the O3 molecule. The only difference is where that double bond is. Is it between the oxygen on the left and the center atom, or the center atom and the oxygen on the right? So there's 2 possible ways to draw this structure, and we use a double-headed arrow in between to show that, hey, it can either exist like the one on the left or the one on the right. In either way, we're using the correct number of electrons, and we're making sure each oxygen has 8 electrons around it. Again, this is what we call a resonance structure. Usually you're going to have 2 or 3 resonance structures to draw.